Andy asked me to talk about plasma waves at Saturn, and I had a hard time. I put the talk together, and I had like 190 slides, so I had to cut it down quite a bit. So I'm going to do a really high-level talk. Because there's just so much data at Saturn and so many different things we can look at. I'm just going to briefly go over the Cassini mission to start with. It was launched in '97 and arrived at Saturn in 2004. It had a 4-year nominal mission that ended in July of 2008. It had a 2-year extended mission, and now we're in the extended mission called the Solstice mission, with the idea to look at the whole season from summer to summer, one hemisphere to the next. We're currently in Rev 201. It's actually, I think, the 203rd orbit because they had sort of a funny counting system at the beginning. The current plan is to end the mission in 2017, the last orbit, Rev being 293. This will, of course, depend on the senior review that's going to happen later this year if we get extended to 2017. The end of the mission is actually a Juno-like mission where we go to high inclination orbit and we actually fly between the rings and the upper atmosphere, just a few thousand kilometers. So we get very close to Saturn and actually sample the ionosphere of Saturn in situ. This is a nice overview plot that I got from JPL, just showing the Cassini mission, each year of the mission out to the planned end at 2017. Shows the number of orbits in each year, the number of Titan flybys, the number of Enceladus flybys, the number of different icy moon flybys, and then the orientation of Saturn compared to the sun. So you can see we went from going from summer, southern summer when we first got to Saturn, and hopefully go to northern summer at the end. This is just an inclination plot for the Solstice mission, 2011 up to 2017. We had an equatorial period. You can see all these Titan flybys. We used Titan to change the orbit trajectory. We went to higher inclination. We're right now about where the blue line is, and we're going to come down over this next year into next year. In 2015, have an equatorial period again with the last Dione flybys and Enceladus flybys, and then use Titan to ramp back up, and then to jump into what's the F-ring orbits, where we're going to fly in the gap in the F-rings, and then into the proximal orbits. This is just a sketch showing the proximal orbits. We hope to have 20 F-ring orbits and then 22 proximal orbits in really close. And this is just a drawing with the orbital periods showing you in between the rings, just outside the atmosphere of Saturn. And the very last orbit, we will enter into the Saturn atmosphere due to planetary protection. And this is a plot Bill Kurth put together showing the orbit 271 in the proximal orbit, rho versus z thing, axes, just to show that we fly in really close to the planet. We should experience the actual, take measurements of the ionosphere. For us, the plasma wave instrument, the upper hybrid measurements, we should be able to get a density for the electrons. Measure the dust, whatever dust is in this gap inside the rings, and also hopefully see lightning or whistlers from lightning from Saturn. The radio and plasma wave science instrument, or RPWS, has 5 receivers. We go from about 2 hertz to 16 megahertz. We have a couple high-rate parts receivers, the wideband receiver and the 5-channel waveform receiver. We can get the wave propagation of the plasma waves with this, but we don't have the time resolution that we have on RBSP, on Van Allen probes that I showed on Tuesday. But we can do a lot of the same type of stuff. We also have a Langmuir probe. We use 3 electric antennas, usually in a dipole and a monopole configuration. And then we have the 3-axis search curl magnetometer. There's a ton of radio and plasma waves that we've detected at Saturn. I'm just going to talk a little bit about a few of them. Margie actually gave a much better summary of the periodicity. I'm just going to show 1 or 2 slides from that. I'm going to show a little bit about the Saturn electrostatic discharges, SEDs, just because that's a way to remotely look at properties of the ionosphere. And then for the actual plasma waves, we see Langmuir waves upstream of the bow shock. We also see them in the magnetosheath. I'm not going to talk about those. We see a lot of electron cyclotron harmonics, ECH emissions, and the upper hybrid, which we use to get the density, and then a bunch of Whistler mode emissions, including auroral Histone with the higher inclinations. So this is just 2 spectrograms showing 2 different orbits. This is an equatorial orbit. This is 2 days. We go from about 13 Saturn radii to about 14 Saturn radii. The white line is the electron cyclotron frequency. This is the SKR. This is the upper hybrid, which Ann Pursoon gets the density from. ECH waves, some Whistler mode course here. This is a low frequency emission that Patricia Schipper actually figured out the coupling between the local plasma and the antenna system. And then for a high inclination orbit, it's very similar. We see SKR, the upper hybrid here shifted just due to the trajectory of the orbit, and this didn't plot quite right. We see narrowband electromagnetic radio emissions, again some chorus, and these are the auroral hiss's that we see. Lightning whistlers. I showed some nice examples from Van Allen probes on Tuesday. For Cassini, so far we've only seen two, what we think is two, and only one of them has been analyzed because the second one is not very good. Ferzan Eklund did her master's thesis back on this whistler in 2006, and I'll show the example here. Next slide. The reason we don't think we've seen more whistlers is two reasons. One is lightning at Saturn kind of comes in bursts, and you can go a year without seeing any SEDs, which is the high-frequency radio emission from the lightning. So first off, there's not as much lightning as at Earth, at least not large-scale storms. The second is we just don't really sample the correct L shells where these storms have been seen for SEDs in the current orbits. Now, in the proximal orbits, we'll get in close enough and we'll sample those L shells. So we expect in the proximal orbits, if these storms are going on, that we will see whistlers. The other issue we have is the reaction wheels on the spacecraft that control the pointing of the spacecraft causes interference in our receivers. And unfortunately, it's sort of in the frequency range we expect to see the whistlers. And it's also has gotten worse as the mission has gone on. So it makes it more difficult to see weaker whistlers. This is the example of the whistler that Ferzan analyzed. It was seen back in 2004, not too long after we got to Saturn. And it was down in a few hundred hertz range. And using the dispersion of that whistler, she calculated that it only made sense if it came from the northern hemisphere at about 67 degrees latitude, which is actually higher than the SEDs are usually storms are seen. And from that, she was able to, in her thesis and in a paper that she published, determine some scale heights and composition information using that dispersion and the propagation path. This is an example of SEDs, Saturn Electrostatic Discharges. This is now, 1 megahertz. Actually, this is 10 to the 6 hertz, so that's 100 kilohertz. This is, actually, no, that's 1 megahertz, sorry, 10 megahertz, and goes up to 16 megahertz. The high-frequency receiver steps in frequency bands of 25 kilohertz, and that's why these things look like sort of like specks. So there's so many in this great storm that they're on top of each other. What's really happening is the lightning is sending out a broadband electromagnetic radio signal, and so as the receiver steps, it's just catching these really short bursts, and they look like little spots. Georg Fischer has done a lot of work looking at these. In fact, he's the expert on SEDs and lightning at Saturn. But by looking at the frequency cutoffs as the planet rotates around or the storm rotates around, you can determine a lot of properties of the ionosphere. This is just a chart he put together that goes up to 2012 of all the SED storms, the number of SEDs per Saturn rotation. And this is the giant storm that happened in 2010, ended 2010 and lasted for many months into 2011. And I mentioned earlier, from the properties of the SEDs and when we see them and don't, and the frequencies, you can determine a lot of stuff about the ionosphere. As I mentioned earlier, we see a lot of ECH and upper hybrid waves. In fact, we see upper hybrid waves on every orbit we get in within 10 RS of Saturn. These are electrostatic emissions that can be quite intense, and we use this to get electron density, just like I talked about on Tuesday with the Van Allen probes. And Ann Pursoon has done a bunch of work on that. We also see use the upper hybrid around the icy moons and Titan to determine the electron plasma density around those. And this is just an example where the white line is what she's digitized to determine the peak upper hybrid frequency is to get the density from. And she has used that. This is an example from her high inclination paper in 2008. These are the orbits, periods she had data for, and she determined models of the electron density contour maps and also the water group ions and hydrogen ions with some assumptions. As I mentioned earlier, we can do this at Titan. This is a Titan flyby where there was a lot of structure in the electron density as we passed by Titan. This is the distance from Titan and the latitude compared to Titan. This is the Dione flyby where we went into the wake of Dione, so you can see the upper hybrid frequency drops down, the density, basically the cavity behind the moon that the electrons have been removed from. And at Enceladus, this is actually approaching the Enceladus plume. All this spiky stuff is from dust hitting the spacecraft. But you can see the upper hybrid actually drops here. The electron density drops. And Bill Farrell and others have written a couple papers to try to explain this drop and the interaction of the electrons with the dust in the plume. As I mentioned, we see ECH waves quite often. With the high waveform, with the wideband, the higher resolution data, we can zoom in and look at structure, and there's a lot of different types of structure in the ECH waves. This is two cases where we see the harmonic just above the cyclotron frequency in the second harmonic. This is actually some Whistler mode emission down at the bottom I'll talk about later. At Saturn, interchange events are important. Injection events where the cold plasma is flowing outwards and you have to conserve momentum and everything, you have to have the hot plasma flow in. And this is an event, and Cassini encounters these events usually about 5 minutes long, maybe minutes long periods where we enter these tubes of hotter plasma. Quite often when we do that, this is CAPS plasma data, the Whistler mode and ECH waves are greatly enhanced and change characteristics. Here you have a background, sort of a weaker ECH wave, and when we enter into this event, the chorus lights up, the Whistler mode emission, and then these harmonics of the ECH waves light up. And this is just a neat, I like this spectrogram. During a Dione flyby, we happen to basically encounter one of these injection events at the same time. You can see the densities dropping because we're entering the tail of Dione, but then all of a sudden it just goes crazy. And so you can just see these tens of harmonics of ECH waves inside of this injection event, and then we exit the injection event. So it's really hard in this period here to determine what's caused by Dione and what's caused by the injection event. Whistler mode waves, we see chorus at Saturn, though the characteristics are both similar and different to chorus of the Earth, and they're also very different inside and outside of the injection events. Has a great deal of structure, a lot of it's His-like, and then we have these emissions that Bill Kurth called worms, which are longer periodic emissions. And then we see auroral His, and the auroral His has both the 10-hour periodicities of the SKR, but there's also a 1-hour periodicity that we quite often see the auroral His. And we also see an auroral His type emission associated with Enceladus. This again is a survey plot of orbit 97, where we came in, we saw Whistler mode emission both inbound and outbound. This is a medium inclination orbit. We go from 20 degrees latitude out to -20 outbound. But what's interesting in this orbit is we basically stay at the same L shell, about 5.9 or so, through most of the inner magnetosphere part here. We get into about 5 RS, a little less higher, farther. But the chorus is nice because we can see both chorus from northern latitudes and then into southern latitudes. And this is the wave propagation analysis done with the 5-channel waveform receiver. It's much lower resolution than the one I showed from Van Allen probes. But as we cross through the equator here at the center, this is wave normal angle. Red is 180 degrees, so K is pointing anti-parallel to the magnetic field. It's red. In the middle here near the equator, the chorus actually gets much weaker and kind of goes away. Then it comes back at slightly higher latitude and it goes the other direction. This just shows that the chorus is propagating away from the equator, has been shown at the Earth multiple times. And Doug Manetti's been looking at that and the amplitude variation and comparing it to models in a series of recent papers. This is the wideband data, the higher resolution data, and I just want to point out at the top of these plots I put sort of how long the time period is, how long the spectrogram is, just because I plotted different time scales. But a lot of the Whistler mode emission is sort of His-like. We do see fine structure quite often, but this is sort of a 1 second, a few second period between elements. Here's a period where we have 10 second, roughly 10 second time between the rising tones. And here we have a 2-hour plot where we're actually seeing about 5 minutes between rising tones. So much different different types of time scale than we see at Earth. And this, I wrote a paper in 2008 where I called this chorus. Jared Leisner has looked at this, and Bill Kurth has called these worms. Has a paper that really should be submitted really soon where he's looked at these in detail, the periodicity of these minute periods. Sometimes in the higher resolution data, here we have tens of second periods, but if you look carefully, if you zoom in, you actually see fine structure on top of these elements in the order of a second. Now, all of these examples are outside of the injection events. And the other comment I should make is we never see these Whistler mode emissions above half the cyclotron frequency outside the injection events. But inside these injection events, you actually see the gap at half the cyclotron frequency, which is really common at the Earth. And also the fine structure gets to smaller timescales. And actually, I only have one sound clip to play compared to yesterday, but we'll see. And it doesn't have a movie like that, so just the sound. So what you hear at first is the ECH waves, the higher frequencies. And then over here, you're going to start hearing the whistlers here shortly. It's that lower frequency rising tone. And I do have to comment, we've cheated here because this is actually 1 minute and 40-second long spectrograms. At the stuff I showed Tuesday, it was like 6 seconds of data, but we've jammed this together, so I've sped this up. So the rising tone you heard there is actually somewhat artificial. This is just some of the other examples during the injection events of the fine structure. As I mentioned earlier, we usually see the gap inside the injection events, so you have upper band and lower band, and then the fine structure is on the order of a second or so. Local time dependence of the chorus or the Whistler mode emissions, we see it over all local times, and we see it from about L shells of slightly outside of 4 out to about 10. This is just L shell and this is R radii. The injection events we see over all L shells, and it's more confined, more between 5 and 8 L shells. And then latitude dependence, we actually see Whistler mode emissions from the chorus up to about 40 degrees up there and then farther out. Overall His, these are produced by electron beams, has usually spectrograms, a characteristic funnel shape. The low frequency component, we actually can observe out to many tens of RS. We can see these very far out from Saturn. The SKR-like periodicity, as Margie mentioned, was detected in the auroral His, and it has a north and a south period. And then there's about 1 hour periodicities that are related to ions and electrons in the MIMI instrument. And you can use the frequency cutoffs to also calculate the electron thing. And this is just an example from an orbit where you can see the funnel shape spectrum. The color bar here, I've saturated it, but then you can see the 1 hour periodicity bursts. Margie showed this thing, but it just shows the upper cutoff can be an estimate of the density, and then the 10-hour periodicity. And this just shows a zoom of the 1 hour periodicities that match up the MIMI electron and ion data. In Solstice, we also see funnel shapes at times. In Solstice, Gurnett wrote a paper in 2011 where he compared the funnel shapes to these electron beams that were detected by CAPS. And Jared Leisner wrote a paper in 2013 when we went through all the 20 Enceladus flybys. He found funnels on quite a few of them. He mapped the funnel shape, did a ray tracing study to see where the source regions could be, and found 2 quadrants upstream of the Saturn flow terminator and downstream of that anti-Saturn flow terminator. In the paper, he suggested that these electron beams could be produced by strong field-aligned currents or possibly Enceladus surface charging. I'm just going to, since Margie did this much better than I was going to do, I won't really talk about the periodicities, but as she mentioned, it's seen in basically everything in Saturn's system has a period around 10.7 hours. And this is a plot that Gurnett gave at the PSG last October, showing the northern and southern periods. And around equinox, we thought they were going to cross, at least Don and everybody, I think, thought they were going to cross because there were Ulysses observations from the last equinox that sort of implied that maybe they crossed. But what's happening is they've sort of, as Margie mentioned, kind of become chaotic, I mean, and sort of centered around the center halfway between the two, and it's not clear at all what's going on. So I'll just conclude there, and if you have any questions, I'll be happy to try to answer them.
Time for a few questions.
So in 2008, 2009, and early 2010, the sun went through its deepest activity minimum in 2 centuries, probably. This had profound effects in the Earth's magnetosphere, the change of the character of the interactions with the solar wind. Presumably you could see those kinds of, or some hints of those kinds of things in the Saturn system. Have you looked at that? Have you sort of, characterized before and after?
I don't know if anybody's looked at it in detail. I've noticed stuff just looking at the data, especially as the sun has become more active recently. The bow shock gets pushed in farther than it seemed to earlier in the mission. I don't know if anybody's really looked at that in detail. I know there has been attempts to look at solar effects on the periodicity. I don't think there is small-scale structure in the periodicities that maps the solar wind conditions, but the large-scale stuff, I don't think anybody's.
It should really be a way of sorting out some of the solar forcing compared to the internal. I mean, nature performed, again, a beautiful experiment for you.
Yeah, you mentioned this 1-hour periodicity in the auroral hiss, and maybe it's associated with ion beams, but do you have any idea of what's governing that period?
I do not. I should go back and read Don's paper, especially since I was a co-author, to remember what he claimed in the paper. That was a long time ago. But I don't remember what his ideas were. But it's quite common. We see it, I mean, throughout that period we were the high inclination.
Okay. The dramatic change of the spectra in the interchange events is really wonderful to see. What's producing the big difference in that spectrum?
Well, it's the plasma. I mean, the plasma conditions changed, and it can drive the waves.
But can you say something about what the change is?
Well, it becomes much hotter on the anisotropic. I can never say that word for some reason. I shouldn't be in this field since I can't say temperature anisotropy. But both Doug Manetti and Tao at UCLA have done work modeling the actual measured plasma conditions, and you can really get enhancements in the growth of those waves. And Richard might want to say something because he was involved with those, with Tao's studies. But it just has to do that the hot plasma conditions are much different than the cold outside, and you can really drive growth of those waves.
Richard, do you want to say?
I'm not sure I can say anything definitive, but I think it's very difficult to actually understand the origin of the waves outside of the injection events because you need a source of anisotropy and high flux to normally generate chorus. And maybe that's why these sweeping rates are so different seen at Saturn than at Earth.